Welcome, everybody. Good morning to the US, good afternoon to Europe, and good evening to Asia. We are here today from 𝘴𝘊𝘐𝘓𝘏, the #1 supplier for ceramic flat-sheet membranes, and we want to talk today about PFAS. PFAS, a big topic, and we are giving just another minute that the people will be able to join. We have more than 45 people right now, and some more are still joining. Today's topic, we want to talk about PFAS removal with ceramic flat sheet membranes, and we split this a little bit into parts. The first part will be about the test at Rome, Georgia. So there we did a technology test to conduct really the best technology to figure out which technology can best remove PFAS. So we will talk about this first, and after this, we will talk about the ACLF process, which is the active cake layer filtration process with the ceramic membranes. And therefore, I have three guests next to me. First of all, I would like to introduce Kai. Kai is the president of 𝘴𝘊𝘐𝘓𝘏, and right now in cold Germany. The other one we have on board is Julius. Welcome, Julius Glöckner. He's the CCO, the Chief Commercial Officer of 𝘴𝘊𝘐𝘓𝘏, right now in Dubai. And last but not least, we have Chris 𝘐𝘠𝘵, the CEO from 𝘴𝘊𝘐𝘓𝘏 US. Welcome on board, guys, and good to have you here.
Thank you, Björn, for the introduction, and welcome everyone today. Thanks for joining. We hope we have something really exciting for you as Björn opened about ceramic flat sheet membranes removing PFAS. Out the gate, we wanted to quickly share the results and then we go into details. So first of all, 𝘴𝘊𝘐𝘓𝘏 ceramic flat sheet membrane technology really proven as the most economical PFAS removal solution in the globally most broad PFAS technology assessment in Rome, Georgia. It was a 4-month pilot, about 3 water sources, and we confirmed over 99-point-something% removal of PFAS at all times, lowest CapEx, lowest TOTEX compared to all available and conventional technology solutions. In a summary, it's a very simple one-step process with the lowest waste volume. This is really what matters, highest recovery load waste volume, and it removes completely the PFAS from the water cycle, not leaving some liquid waste that goes back into river, really completely removing the PFAS, and it lowers the ratepayer savings because of the better economics, of course. And last but not least, it's a very modular solution able to retrofit any existing water treatment plant, whether it's a sand filter treatment plant or a polymeric membrane solution plant, easily replaceable. The agenda today, why is PFAS removal important? The results at Rome and what we really did there, how active cake layer filtration works, and some of the key advantages to sum it all up about ceramic flat sheet membranes compared to the commonly available solutions. And 𝘭𝘠𝘵 will kick us off, Chris 𝘭𝘠𝘵, with why PFAS removal is important. I'll stop sharing here. You can take charge of the screen.
One more thing before 𝘭𝘠𝘵 start. As I said, welcome everybody. We have meanwhile more than 60 people on board. If you guys do have any further question, put them in the chat. We will collect them, and in the end, the expert on board will answer them. So now it's your stage, 𝘭𝘠𝘵, and all the best.
Unmute myself. Good morning, afternoon, and evening to everyone. Thanks again for joining us. I'm going to try to fit about 2 hours worth of information into 20 or 30 minutes here. So bear with us as we skim over some fascinating results from the tests that we've completed in Rome, Georgia. So the first thing to understand, especially the landscape in the United States with regard to PFAS, is literally all over the place. We've got the Federal Environmental Protection Agency taking steps to put together a nationwide roadmap. That's been a slow process. Individual states throughout the Northeast and the West have come up with their own PFAS standards. So it's a little bit of a moving target and really tough from the perspective of a utility to figure out what you need to be doing, what you need to be testing, and how you're ultimately going to solve the problem. So credit to the Environmental Working Group back in January of 2021. They put together a map of the United States showing where PFAS contamination had shown up either in the groundwater, surface waters, or industrial discharges that were known. And you see those kind of noted throughout the United States, actually just more highly concentrated in areas where testing had been done. As testing picked up through 2021, you'll see here's the new map for October of 2021. So not only did the dots fill in, but a lot more states have positive contamination results shown. And from the perspective of the 𝘊𝘶 pilot test, I also wanted to point out what we're looking at is the Coosa River Valley, and where it originates in Northwest Georgia and flows through Alabama. If you look in earlier 2021, before testing had been done, Alabama was relatively unscathed. You see that picks up quite a bit as the testing picks up. So it bears the question, you know, as a consultant or a utility, an operator of a plant, what do you do with PFAS? There aren't really viable solutions. We see PFAS contaminants showing up in landfill leachate, and as I mentioned, surface and groundwater, and it gets reintroduced as it flows through wastewater treatment plants. So it's going to end up right back in the streams where we've taken it out. And none of the conventional treatment processes work. Conventional sand, polymeric membranes, you know, just aren't equipped to get that out. And even GAC and reverse osmosis, while they will work, they're expensive and they've got large waste streams that come with them. So the 𝘴𝘀 solution really combines a couple of known technologies, very well vetted technologies, and we come up with a low pressure, which, you know, obviously requires less energy, less chemicals, less mechanical force to get the solution implemented, a lower capital expense, lower cost up front. It's an easily maintained one-step process, and we'll get into the details of that a little more. And the design really lends itself to rehabilitating existing treatment plants or putting in a side stream system, and it completely removes PFAS from the water cycle. So you end up with a small side stream of treated waste that is easily dewatered and disposed of. So specific to the 𝘊𝘶 pilot test, this is a little graphic of the city of Rome. You can see two rivers converging to form a third. So the 𝘊𝘆𝑚 River intake, that comes from high Northwest Georgia, gets pumped to the water plant, and the 𝘊𝘶𝑚 River intake. So, you know, two sources with different levels of PFAS contamination. They form the Coosa River, which then flows throughout Georgia and into Alabama. You can see just kind of generally what the PFAS composite contamination was in the 𝘊𝘆𝑚. Averages about 442 parts per trillion is what the RFP, or the information leading up to the study, indicated from 2019. You see, we actually saw over 1,300 parts per trillion. Turbidities are manageable. Etowah has less overall PFAS, but still a considerable amount. We saw 82 parts per trillion in 2021 during the test. So our objective was to take out as much of that as possible, and the city and their consulting engineer brought on nearly a dozen technologies. And you see here some pictures of kind of the circus tents that were put up over all the different technologies and the intermediate tanks. So their objective was to find cost-effective and technically reliable solutions. And of course, a lot of the old guard was there, as were 𝘴𝘀 and our active cake layer filtration process. First time demonstrated on a large scale globally. So the other objectives were to define some suitable pretreatment and also remove all the PFAS contaminants below detectable limits. So at the time all this was put together, detectable limits were about 9 parts per trillion. And you see later on we've got test results that are more in line with you know, less than 1 part per trillion is how they were measured down. So a quote here attributed to Tom Freston: "Innovation is taking two things that already exist and putting them together in a new way." And that, in a sense, is what we've done with the active cake layer filtration in our PFAS solution. Adsorption is not new. Flat sheet ceramic membranes are not new. Both vetted technologies, decades old, but simply putting two well-recognized effective technologies together is what's led to our solution. Again, so it's not experimental. It's nothing new or cutting edge. It's just the innovation of putting two very stable, dependable processes together. So ultrafiltration, powdered activated carbon, really only possible with the 𝘴Filtech design. And we're able to remove not only PFAS, but all kinds of dissolved contaminants from TOC, things that cause taste and odor problems. This is an idea of what it looks like, the powdered activated carbon layer on top of a ceramic membrane. Obviously, the ceramic membrane is small enough pore size to exclude the powdered activated carbon, but you can see where every drop of water needs to pass through this layer before it can be pulled through the membranes, which allows for high efficiency contact with the powdered activated carbon. The summary of our results, we were able to remove more than 99, and actually it was sometimes 100% PFAS removal below detectable limits, a 99% recovery rate. It's a one-step process. The metrics bore out that we were producing a permeate with very minimal pretreatment from anywhere from 0.015 to 0.02 NTUs of turbidity, very low pressure loss, from 0.5 to 2 PSI across the membrane. The powdered activated carbon actually enhances the performance of the membrane. So that gives us an operational advantage there too, keeps the power costs low. It's a green, sustainable solution, as we mentioned, completely removes PFAS from the waste stream. So why is powdered activated carbon so much more effective than granular activated carbon or reagglomerated, or RGAC as we call it? And what you see from this slide and this visual representation is that the powdered activated carbon is actually much smaller. So everybody, intuitively knows that you're going to get a more efficient filtration process, but also the specific surface area of powdered activated carbon equates to about 25 times the specific surface area of granular activated carbon. So you've got 25 times the sites to adsorb particular contaminants, be it PFAS or TOC. This was all vetted, invented, if you will, proven in a laboratory environment prior to this. And you can see the cake layer on the outside of the powdered activated carbon. And what we're able to take in terms of raw water quality versus permeate is really quite outstanding. So not only are we removing the invisible contaminants, but producing drinking water quality permeate that requires no further treatment, no remineralization, no additional work on it. So some of the third-party, independently verified and produced results regarding breakthrough compared to GAC, compared to lead and lag resins and different types of powdered activated carbon. You see with the longer chains, those of you that are already well immersed in the PFAS world, PFOS is C8, so a little longer chain, easily adsorbed, not so easily on some of the other membrane. You see it to the left, a pretty quick breakthrough in some GAC and some other media. Again, with a higher concentration, we perform very well, multiples of the breakthrough time that you'd see as far as treated bed volumes and the multiples there that we can achieve. So in summary, we're getting about 3,300 times the absorption, 3.3x, 3,300%, I should say, higher bed volumes and a shorter empty bed contact time. So a much more efficient process. This shows with shorter chains, some C6 and the Gen X compounds that are a little harder to remove typically. The Rome pilot test itself, as I mentioned, there were nearly a dozen different technologies, and understand that all of these technologies were either pre-treatment or they were PFAS removal focused treatment systems, and they all needed to be run in series. So there is no one solution on this slide, save 𝘴 Filtech, that could take limited pre-treated water and run it through a filtration process to remove PFAS. So we were pretty excited to be listed in both the pre-treatment and the PFAS mitigation technologies. And I should say that slide would also lead you to intuitively understand that we were the lowest total capital expenditure and operating cost because of the simplicity of the system. These are just some photos, kind of set your imagination of what this pilot test actually looked like. Again, there were container after tank after tent, and a labyrinth of hoses. There was a common discharge for everybody's wastewater and a common discharge for everybody's treated permeate. The sources, the two rivers, as we mentioned, that the city pumps from were pumped to a central tank and then distributed to all the pilots, independent of the full treatment process. So there was a blend tank where we either got water from the 𝘊𝘆𝘗𝘌𝘍𝘐𝘓 for a month, a blend of the two, or water directly from the 𝘊𝘠𝘶 River for another month. So it's actually a great layout, really well executed by the city and their engineer. And I think it proved what they were looking to prove as well. This is just a snapshot to show you what we did inside of our container unit, with a little bit of pre-treatment provided by a disc filter fed right into our normal process. Interestingly, we didn't need to add any further chemicals except for the powdered activated carbon. So there was no additional flocculation or pH adjustment required. We simply went straight through the membranes and achieved the kind of results that we achieved. Okay. Through the different phases, here you can see just across the bottom, we identified each of the PFAS compounds that showed up positively in the raw water results. And you can see on this particular day, when we were getting 1,300 parts per trillion, we were removing 99.9 to 99.4% of all of that, all those contaminants, which got us typically below typically below 5 parts per trillion, certainly well below any of the state or
action levels,
EPA standards. Okay. Phase 2, same as when we had the mixed source water. You see anywhere from 800 down to 275 parts per trillion of feed water, and that resulted in 99.4 to 99%, 99.7%, excuse me. There's also a couple illustrations there that I think that are helpful to understand what the tank looks like, a small filtration tank like this before we add powdered activated carbon, and how the carbon layer actually looks on the surface of the membranes when they're in use prior to backwash. Okay. Phase 3, same thing. This was straight from the 𝘊𝘶 River, so 99% to 100% removal of all short chains. And when we got 99%, we were down to 0.4 parts per trillion. 0.4 of a part per trillion was the result. So pretty good. Here, I wanted to just let this sink in a little bit. Obviously, we've got the metrics from the full scale, or I should say the metrics from the pilot test, where we were able to achieve everything on a small scale, which those of you that have done this before know it's difficult to achieve a full scale water treatment plant evaluation on a very small scale. But those were the gross numbers there. On a full scale, in our projections based on other operating conditions and projects we've already implemented, you can see PFAS removal will be 99% or greater, a recovery rate, again, so limiting your waste stream, both water and saturated powdered activated carbon, that'll be in the range of 99% as well. The kilowatt per hour per 1,000 gallons is minimal. Again, we could almost run without pumps, simply using gravity through the membranes. They're so efficient and support such high flux rates. So our overall cost is going to be about 1/4 per 1,000 gallons, which includes powdered activated carbon, chemicals, power consumption. Really quite compelling case for operations. That is a quick summary of what we did in Rome. Julius Glockner is now going to take over and walk us through how the individual technologies work. And take it away, Julius.
Excellent. Thanks, Chris. Really appreciate it.
Thanks a lot, Chris. Just one more word, Chris. We have, or to our audience, we have a lot of comments and questions in the chat. Don't worry, we will all answer them at the end. There were a lot of questions about the Rome test, and I'm pretty sure there will be even more after Julius has given his presentation. So just wait another minute until Julius is ready, then we will go through all the questions you have. Julius, your stage.
Thank you, Vivian. So how Therafiltic works, meaning how ceramic flat sheet membrane works, and how does active cake layer filtration work? First, let us take a quick stab at where ceramic flat sheet membranes are on the scale of filtration options. We are right in the 0.1 to 0.3 micron pore size. You can see that here on the slide illustrated. And how the technology works, we are a submerged solution. We are out to infiltration. That means the membrane is underwater. We are operating with suction pressure, and we're pulling the water through the membrane layer into the inner water channels out the end cap. And backwash obviously works the other way. We push clean water into the membrane, and that process removes the layer that is on the membrane to free the membrane from blocking. In the module, in the Therafiltic module, we have 34 plates aligned, and you can see how the water actually flows in operation. Yes, the water flows upwards because the tower is stacked underwater, and the water flows to the main header pipe, and then backwash the other way. We push the water into the module, and from there it gets hydraulically evenly distributed to all membranes. In an actual tank configuration, this is how it looks. You can see the water traveling upwards during filtration to the main header pipe, and then out, as Chris mentioned, essentially via a transfer pump or gravity. We usually operate between 50 millibar and 400 millibar. Specifically, that's 1 psi to 6 psi. In Rome, it was closer to the 1 psi essentially at all times. Backwash then is 2 times the flow. And our filtration cycles are usually between 2 and 12 hours across all applications: sewage, tertiary treatment, surface water, groundwater. On the PFAS removal side specifically, we tend to be on the longer cycles because we want to minimize the waste volume and maximize recovery rates. So there we have 12 hours filtration cycles in Rome. To give you a feel for how a plant looks like at full scale, this is an image of the 35 MGD plant. You can see on the left side the full plant, and on the right side one of the trains with the Therafiltic towers embedded in it. And it's important to highlight that while this application is really about PFAS removal, ceramic flat sheet membranes are really an accepted standard even without active cake layer filtration across all kinds of applications, as mentioned: groundwater treatment, surface water treatment, seawater, tertiary, sewage and MBR, unlocking operational benefits and economic savings for the operator and the asset owners. Because of the uniqueness of the material, we have a large degree of freedom to incorporate treatment steps combined with the ceramic, as Chris mentioned earlier, combining adsorption directly with the ceramic, and that's really a unique feature of the ceramic flat sheet membrane. And here we're going now into the active cake layer filtration. First of all, why is it called active? Because the layer has an active function. We are bringing something into the water that layers onto the membrane that actively removes contaminants. So, for example, we remove radioactive isotopes by adding a layer of hydrous manganese oxide on the membrane as a layer, and with that removing 97% of radium. We can add powder activated carbon to remove anything that carbon actually adsorbs. And this is only possible with submerged ceramic flat sheet membranes. Because of the TSS limits of submerged polymer membranes, you cannot put any layer on it. And here, as the picture illustrates, you need a submerged solution. You cannot have a pressurized solution. When you have something submerged, you have ambient pressure on the outside of the membrane. That means the active cake layer is not getting compressed on the membrane. We always call it, it's like a virgin snowfield. It's very loose, water can easily pass through, and therefore the membrane layer, or the active cake layer, removes the contaminants. In contrast, if you have a pressurized system, it's like walking on that snowfield, and you compress the snow onto the ground and it blocks the cake layer, it blocks the membrane. So it only works with ceramic flat sheet membranes in a submerged environment. And we also wanted to share a little bit that this is actually very vetted processes. Just a quick dive into the history. Our team actually invented the ceramic flat sheet membrane design in 1993 and then launched the commercial module, the commercial solution in 2005 and built also globally the first treatment plant with ceramic flat sheet membranes. This is how old the technology is and has really been in place. And from there on, led key milestones in the development of the technology and the processes, and specifically there, as you can see in the red box, the active cake layer filtration. And with this process, we've executed already over 100 million gallons per day capacity. In the picture down here, you can see the membranes layered with hydrous manganese oxide, removing radioactive isotopes that are actually much harder to remove than PFAS, really as a standard application, having it shown over and over again about the reliability of the process and the economic advantages of this process. And this is really where the rubber meets the road. At the end, you want to save dollar and you want to achieve the water quality. And for sure, as mentioned, the picture prior to that, layer with hydrous manganese oxide, but really we can use any adsorbent as a layer on the membrane. Powder activated carbon lends itself as a perfect adsorbent. Why? Because it's widely accepted across the water treatment industry and it has phenomenal adsorption capabilities as it pertains to TOC, VOC, pharmaceutical toxins, anything that causes taste, color, odor issues, and of course also PFAS and PFOA and any type of Gen X and short chain PFAS molecules really being removed here up to 100%. And here you see the cross section of the membrane again, how that works. And that layer, that adsorption layer really works with any adsorbent that you can layer on the membrane here visualized. Also, we work with different membrane materials, silicon carbide as well as aluminum oxide. Both of them have different advantages and different applications, and 𝘴𝘂𝑡𝑒𝑐 is really there to empower the system integrators, the asset owners, the operators to make the right selection, implement the right processes to effectively remove their treatment goals. As part of 𝘴𝘂𝑡𝑒𝑐's innovation, we've also developed 4 years ago a new cleaning strategy, and not CIP and CEB that are commonly used in submerged solutions, but a process that we call cap clean. Cap clean because the capillary force of the membranes are actually doing a lot of that work. So we drain the tank and then we do a backwash to remove most of the layer, and we shower the membranes down with, as you can see here on the left side, a water jet that really flushes that cake layer down to the bottom of the tank out the drain. And when the membrane is blocked or scaled because of biofouling or because of scaling, we can put chemicals directly from the top of the tower onto the membranes, and the capillary force sucks in the chemicals, and we only have to wait a couple of minutes to fully recover the membrane. This is the beauty. We always explain this example that if you clean your bathroom, you're not filling the bathroom with the chemical solution and wait for hours. Like in the conventional cleaning process, you go there and you spray chemicals directly on the stain and you wipe it off and it's done. And we are simulating that process. We're putting much higher concentrate of chemicals onto the membrane where it's needed, but in total, a lot less quantity than if you have a chemical solution and the membranes are bathing in it for a long time. And in summary, we wanted to highlight a few key advantages really that ceramic flat sheet membranes unlock for our partners and for the end customers. And just to go through a couple of slides here, and they're connected all to PFAS removal. As you can see, then we are combining really the best of both worlds. We get the robustness and the chemical resistance and long life of inorganic materials, of sand filters, and we're getting the high water quality of polymeric UF membranes, especially polymeric membranes in the beginning, and then later on they decay with chemical treatment. This doesn't happen at 𝘴𝘂𝑡𝑒𝑐 or at ceramic flat sheet membranes, so we really get the best of both worlds. And another key advantage, we always look at the economics at the project level. And if you see, in many cases, treatment is not easy. Multiple steps are required. This is an example of a more complicated seawater treatment project. And we can cut down these process steps and simplify the process solution. And in the process, reap enormous cost savings on the CapEx side as well as the OpEx side, and remove a lot of headaches in simple operation. We empower system integrators and operators to really get the best economics out of the solution. So we have a modular system that fits any existing tank design. We have a robust solution that gets up to 20 years of life. It's a reliable operation that is resistant against peak events and chemical cleanings, because we know operation is in 1 year different than in the previous year, and you can never control all factors. It's a simplified treatment process as one-step solution, and in total, it's a lower total cost of ownership, and that's really what matters. The beauty is that with these emergent contaminants popping up all over, as Chris showed earlier on the map, right? The more we test, the more we identify to be treating. We don't need to build new water treatment plants. We can use our existing assets, our existing infrastructure, and simply retrofit the sand filters, for example, to address the PFAS problem. We can either on the left screen drop the modules directly into the filtration tanks, or we have a tank in a tank design where we assemble the tanks offsite for quick installation. On-site, we can do train by train without interrupting the operations. And by doing this, we can actually also increase the water capacity of the treatment plant on the same infrastructure that is there by typically 2 to 4 times the capacity, get better water quality as we're in the ultrafiltration space, and we remove the PFAS. So this is really a beautiful solution for all of the assets across the United States, and where we have PFAS issues, where we use what is there. We don't have to build a new plant next to it. We don't need new land, new permits. We simply rehabilitate what's already there. The same holds true for any type of polymeric UF membrane solutions. Doesn't matter what kind. We can do a direct replacement. We use the same pumps, the same pipes, the same PLC, and we achieve an increase in recovery rate, lower chemical consumption, lower power consumption. We are resistant to peak events when there are plant upsets or upstream issues. And at the end, a lower total cost of ownership while addressing the PFAS problem. We really don't have to build an RO at the end of the plant or a GAC plus an ion exchange. We can simply solve it with a replacement plus powder activated carbon dosing. All in all, I think reliability is something that we really come across when we speak with operators, and this is so important, and ceramic membranes are known for reliable operation. Being resistant against high TSS, high NTUs, algae is not a problem, as you can see on the screen. Oil in the feed water is also not an issue. Hot water is not an issue. Hard is not an issue. You can go down this list. Ceramic flat sheet membranes really provide a robust solution to address reliability issues of any plant operation. A more and more important topic that is highlighted is really the sustainability factor. ESG is a big topic, and ceramic flat sheet membranes, because of the low power consumption, the less frequent backwashes, the higher recovery rate, the longer lifespan, we are able to provide a more sustainable solution as it pertains to ultrafiltration. And this is, again, a very important key element in decision making these days, so we want to highlight this. Serafiltic and this entire ecosystem is really the technology provider. We are empowering our partners who are system integrators, contractors, and operators to deliver successful projects using ceramic flat sheet membranes. We're doing this providing the entire technology solution. That means the ceramic flat sheet membrane towers. We provide the engineering support to build the plants, to design the PFAS removal solutions, to put everything in place, or for the system integrator empowered to put it in place. And we help with all the process settings and process optimization from small scale all the way to large water treatment plants. And in conclusion, to sum it all up, and then we can open it up for questions, ceramic flat sheet membrane technology with active calculated filtration is really the most viable solution to address our PFAS challenges. With all the key benefits that we mentioned, it should be considered, and it's going to be a standard in addressing this issue. And it is already a technology standard with and without the powder activated carbon calculated filtration in drinking water plants, in tertiary treatment plants, in industrial application. And we are more than happy. We invite you to contact us so that we can show you at your site how everything works. We can drop off pilot units, come to site one day with a small suitcase unit, and really validate the techno-commercial advantages of ceramic flat sheet membranes across all applications, and specifically PFAS. And with this, our content presentation concludes, and we can open it up for any type of questions. I see already in the chat 23 comments, so maybe Björn, you take us through and just go one by one. We leave it up to you how you choose and pick.
All right. First of all, thanks a lot, Julius, for the introduction into the ACLF process. To the audience, yeah, you had sent a lot of questions into the chat, and we will go now directly from the beginning to the end. By the way, in a few minutes, I will share also the link to the full Rome report. which you then can download and can have a look into this for your own as well. But let's start with the first question. I think this goes directly to Chris. Chris, the first question was for Nick, and he said, is the 99+% removal all PFAS, or is it selective to the long and short?
That's all PFAS. There was only, I want to say it's a PFBS maybe that stuck around longer than others, but for the most part, and especially when we were well-tuned after we've been operating a little while, it was 99% plus for all compounds. And we did no selective removal or selective accounting of how the contaminants were removed. Specifically, we just added up, the EPA 533 and 537 are two different reporting methods. They actually did the lab test with both methods, and we took the less advantageous of both questions, so the higher values of each, and added all that together to come up with our removal percentage.
Perfect. This
So
leaves
yes, all short chain as well.
Okay, yeah, that was a summary. Okay, got it. Let's stay with you, Chris. There was another question from Nick. He said, once PFAS is concentrated on the membrane, so that means if it is on, are the membrane able to be regenerated or are they incinerated? I think.
Yeah. So just to be clear, the PFAS is concentrated in the powdered activated carbon. The membranes remain intact, and there's no regeneration or incineration or anything of that nature. So the PFAS by its very nature is soluble. So anything that were to break through the carbon actually goes right through the membranes too. So there's not a case where the PFAS accumulates in the membranes per se, but each time the entire system is backwashed and that small amount of waste goes out. And again, it's a very efficient backwash process, not at all like a conventional plant or polymeric membranes. Very efficient backwash process. That small stream of waste, including the powdered activated carbon, goes out for waste treatment.
Yeah, there was another question from Ed, and he was asking, I think this fits directly now. What is the media lifetime, or the lifetime especially? I think we are talking here about the ceramic, and I think now the answer from Chris.
Yeah, so as far as the ceramic lifetime goes, the standard warranty is 20 years, and there is nothing in the water or wastewater treatment, any range of pH or material that we might throw at them in a typical waste stream that's going to impact that. With regular backwash and occasional cap clean, those membranes will function unabated for 20 years.
Yeah, maybe to highlight this one quick addition to Chris's question there on the PFAS process and the incineration and removal and so on. Just to explain in a high level, maybe the process, we after a backwash, we remove the layer, we bring a new layer on the membrane, and we do this every filtration cycle. So we bring the layer on the membrane, we filter for about 12 hours. This is all calculated depending on what's in the water and what we want to actually remove. And we also calculate how much powder activated carbon we must bring onto the membrane layer until the powder activated carbon reaches its absorption is fully saturated, right? And when it's fully saturated, then we bring a new layer on. So let's say 12 hours later, we do a backwash, everything washes down. As Chris said, this very limited amount of waste then gets washed out, and we bring a new powder activated carbon layer onto the membrane. And the key here in this entire equation is that because of this high adsorption effectiveness and efficiency of powder activated carbon, in total, we use less unit of weight or less carbon than a GAC would to remove the same PFAS. Right? So yes, we bring a new layer on every 12 hours, but it is so thin, a fraction of a millimeter effectively, right? And we replenish it, but in total, we have less carbon used over the course of the year.
Thanks a lot, Julius, for clarification. This also answered the question by John, how long does the PEC last before it needs to be replaced? So the answer is clearly 12 hours. So every 12 hours.
Well, it's calculated from project to project, and it depends what's in the water, but we try to stretch the filtration cycles as long as possible to maximize recovery rate, yes.
Sure. One more question, Chris, to Rome, about Rome. Inlet and effluent from the DOC level, do you have any numbers?
Yeah, no, that was not tested. And we relied pretty heavily on the city and the city's consultant for the lab testing. We did some outside testing, but ours was limited to PFAS removal and breakthrough and dosage calculations. So we didn't test the DOC. The TOC, we figured out early on in the process that we were removing roughly 70% of the TOC, but it was fairly low coming in and fairly low going out. And there was a little bit of competitive adsorption with the powdered activated carbon. So that was the reason for us wanting to identify exactly what that factor was so that we could calculate the dosages properly for PFAS.
Okay. Piyush was asking the question about the specification of the PEC. Can you say something about this?
Can you restate that?
The specification of the powder carbon.
Oh, the powdered activated carbon.
Yeah.
We actually used a 𝘴𝘆𝘆 Darko S51, which is a washed carbon. We also experimented separately with an unwashed carbon that 𝘴𝘆𝑆 provided. They're very gracious in giving us lots of samples to use and test the effectiveness. But we stuck with the Hydro Darko B and the S51 by 𝘴𝘆𝑆 for this test. But we've been successful with several other manufacturers as well.
Okay. There was another interesting question by John Dyson. He was asking, how do you separate the river solids from the powder activated carbon so that you can reuse it?
The good thing about powdered activated carbon, it's cost effective enough that you don't try to reuse it. It actually goes out and gets dewatered as part of that small waste stream. The interesting thing, I think we need to differentiate between granular activated carbon and trying to remove an entire bed of that and regenerate that much media, and looking for breakthrough at 9 months or 18 months or whatever the case, and all the downstream safeguards against that, because the powdered activated carbon is used so sparingly and in such a targeted manner and replaced so often. We can literally design the process so that you never have breakthrough and the minimal amount of carbon is used. So the waste disposal, while it's going to be a material quantity, especially in a plant as big as Rome, it's 18 million gallons a day, it'll be a material quantity of carbon. It'll be far less than the other waste streams that you'd see in alternate technologies.
All right. I think we talked about SIP cleaning. I think you answered the question pretty well. Let's jump to the next from Sama. How will you perform the regeneration of the powder activated carbon ceramic membrane? Additional, how you are planning to deal with such membranes at their end of life if you discard them while they are loaded with PFAS adsorbed on PAC particles? So what happens with the powder carbon?
Chris, you want to take this or?
Yep, I can. The membranes themselves won't be impregnated or loaded with PFAS. As we mentioned, that'll all be in the powdered activated carbon, and that's cleaned off at every backwash cycle. So in 20 years, what we'll do with the membranes, that's a great question. If they last longer than 20 years, we'll delay that.
Hide the bathroom.
Yeah, exactly. The PFAS itself, though, we are exploring and working with other partners on a PFAS final destruction. And again, we've solved one part of the problem. I think everybody's natural curiosity automatically goes to, well, what's the ultimate destruction solution? And there are people working on that with us and independently. But I think the key thing to remember there is, if you're going to deal with the problem, how concentrated can you get it, and how small a volume can you reduce it to, so that the final solution, it's always a volumetric equation. So if I give you, 8 tons and 1 million gallons, or 1 ton and 300,000 gallons, it's obviously going to cost a lot less to treat the lower quantities. So that's our objective in the front end. I think the urgency is to get the contaminant out of the drinking water, and then work with other folks as good technologies come along to create that final solution for PFAS destruction.
To throw something else in there, there's also planned downstream further dewatering of the 1% waste that we have to get it really down to 20% concentration of the powder activated carbon. And then by this concentration, there's actually still some energy in an incinerator. So it becomes actually very cost conducive to dispose of the powder activated carbon through incineration process. And that seems to be currently the most viable path.
Yeah, and this is also, I think this answers also a little bit the question from Zara, how long does a PEC last and is it recyclable? I mean, you can get energy out of that, right? So, I mean, it's activated carbon, right? So you
exactly, and you just need to get it dry enough, which I think there's plenty of literature out there that with dewatering, you can get to that level. And this is part of our design solution. It's not part of our scope, but what we recommend. And as Chris mentioned, there are plenty of companies right now that are working to actually destruct the PFAS. I think it's an inherent limitation right now that every technology is subject to. And our objective is to minimize that waste volume to be able to cost effectively deal with it. And secondly, to make sure that we really capture the PFAS and remove it from the water cycle, not that we are left with a huge liquid waste stream that ends up in the groundwater or in the rivers or in other places.
Thanks a lot. There was another question from Zama, he or she, I don't know really. Sorry. How do you cross-link PEC with ceramic membranes? Maybe you can explain again. I mean, we already discussed this.
How do we what?
Work together? How do you cross-link? How do you bring both things together?
PEC with the ceramic.
Correct.
Yeah, at the time, or maybe Chris, you can explain it in your own words.
Well, I was going to say they don't actually. I think he's thinking of something different. It's not a permanent attachment. It's a hydraulic attachment where the powdered activated carbons introduced violently into the influent of the dead end filtration tank, and through the ideal hydraulic design of our modules and our membranes, it's a very efficient suction, if you will, that brings the path of the water and the carbon to the surface of the membrane, where it's adhered through the, that transmembrane pressure is also what holds the carbon in place and forms that bed. So there is no chemical or physical linking other than the hydraulic forces of the water flowing through the membranes. Yeah. And it's it's key. If you look at our membranes, one of the competitive differentiators is almost perfect hydraulic performance, in that each plate and each square inch or square meter of the plate gets uniform hydraulic flow throughout. So we're not getting hot spots or shortcuts. And when properly calculated, the amount of carbon that we add to the tank is almost 100% used and, if you will, stuck to the outside of the ceramic plates during the filtration cycle.
Perfect.
That's how the cake's built.
Perfect. I mean, how often you remove the cake layer? I think this was already discussed. What happens if the membrane breaks? How do you identify this?
So we have integrity tests, we have leakage tests, we have all kinds of bubble tests to show if there's an issue. But the reality is that unless it's a ceramic, right, it doesn't like to be dropped on the ground. So if we don't do this, usually ceramic should not break. So now I'm escaping on the question. What was the actual question? What do we do if a ceramic breaks? We take out the towel, we take the module out, we open it, we replace the one membrane that is broken, and we put it back in. I can see where this question comes from, because the operators we talk to, they're bugged with daily fiber breakages on the polymeric side, and I can tell you that we don't have that problem. This is actually one of the key value propositions of ceramic flat membranes. No more fiber breakages. Just don't drop hammers into the filtration tank and you should be fine.
Perfect.
When we spend time with operators, who are running polymeric membrane plants, I ask them, do you know how we pin our membranes? And they of course want to know. And I tell them we don't. It's not necessary. That's a flaw. That's a flaw in your current product. It's not something we deal with.
All right. Sarah was asking, what is the maximum oil concentration?
Boy, let's say this. I think if we get over 1,000 milligrams per liter, we would want to talk about if it makes sense to have a skimmer upstream. So there's effectively really no limitation. It just is a question of what makes hydraulically economic sense. We do projects in several hundred milligrams per liter with feet in the oil, so this is not a problem.
Perfect. There was one question from Steve. I think it's very in detail. I think for his application, we sip in one step with nitric and PAA peroxide blend. Would your ceramic and materials be compatible?
I don't know the answer to this question, to be honest. If it's okay, we'll follow up on this and then just get back in writing.
And I think Julius already mentioned this in his presentation that we have these skids to go on site and test directly. So I think this will help to answer Steve's questions. How effective is it for short chain? We already talked about this 99. What is the flux for the membrane? What flux are you running at Rome, for instance?
Yeah, Chris, maybe you can talk about Rome and then also the broader range that we typically target.
Yeah, in Rome, the target was 300 liters per meter per square hour. So, liters per square meter per hour, 300 LMH. In U.S. terms, take 58.8% of that. So, probably closer to 160, 170 GFD. What the flux rate is kind of like the question of how long a ladder do I need? And my next question for you would be, well, what are you trying to do with the ladder? So it depends a lot on the contaminants in the water, the temperature of the water, the other conditions, what kind of pre-treatment is available or needed, and we can adjust from there. So in an MBR setting, we'll be as low as 40 LMH in replacing polymeric membranes where there's good pre-treatment already. We've got several designs at 700 and 750 LMH. So that's, 441 GFD effectively at the top end for a good drinking water application.
Anything to add, Julius?
No, this was just perfect.
Perfect. Okay, Niranjan was asking something about flux. We answered that. Frequency for cleaning, we answered that. Lifetime for membrane, already Chris mentioned 20 years. Yeah, Nico, 12 hours operation PEC is replaced with the backwash. Also, Julius answered that. What we do with used carbon, yeah, we already said this, right? There's some energy out of that. Julius mentioned this as well. Oh yeah, for Chris, what were the influent PFAS concentration?
Yeah, as for Martin, when you download the report, you'll be able to see those individual influent broken down by PFAS contaminant, by different family. And so you'll be able to see there, depending on which river they were pulling from, there were more long chain and more short chain in them respectively. So you can see that mix.
Yeah, and I already put the link into the chat so that you can download directly now the full report from the web page.
Very good.
From Nick, that was interesting. Does the thickness of the powder carbon layer increase as the PFAS value increase, or do you decrease flow per cell? That's a very specific one, Chris.
Yeah, no, well, I think it could be either. Right. So what we're trying to do is maximize our time between filtration and get just the exact amount of carbon, maybe with a little contingency, into the tank. The thickness of the cake will be directly proportional to how much we add initially. And what we saw in Rome is that if we could vary that a little with what we knew the loading rate was coming out of the river, that the number of sites you could adsorb a PFAS molecule needed to be increased if you wanted to fully utilize the carbon. So the cake layer can get a little bit thicker, certainly. It didn't need to be much thicker. Or you could decrease flow, but understand again, if you're designing on a large scale, you can't decrease flow too much because you've only got certain amount of surface area of membrane to flow through. So if you're going to reach peak capacity, you need to be at your design flow.
Perfect. I think you found also a new customer. Piyush mentioned that he's using right now 𝑴𝑒𝑚 and that he can now use ceramic, and he's happy there. He said that's great. So we have a new fan. So, but anything else? Let me check. covered. This may have been covered by the economics of 𝘴𝑒𝑟𝑎𝑓𝑖LTAC PEC for PFAS removal are better than for traditional GEC systems. Correct. Yeah, I think you just mentioned this in the first slide from the Rome report, right? So the best TCO, sorry, total cost of ownership. Julius?
Yeah, on top of this, I think the GAC in itself is just limited, able to really remove the small PFAS. The larger particles don't allow for the close contact of the carbons being together, and don't have the specific surface area that allows for the adsorption effectiveness. So all in all, we simply achieve higher removal effectiveness and efficiency with powder than we do with GAC. Especially for the short one. And this only really works when you actually put this in a fixed bed configuration on the powder, right? From literature, we know, just as an example, if you dump a bunch of carbon in a contact tank, you get about 20% PFAS removal, right? So the magic is that you stack the powder activated carbon into a fixed bed to create the smallest contact angles to each other, right? Or the contact spacing between the particles. And that allows for the highest removal effectiveness and efficiency.
Right. Yeah. Nico was answering about OPEX impact. I think if you download the report, I think this is clearly mentioned there, how it is, how the PEC is impacted. So what about ozone? What about ozone and the ceramics?
No problem. We love it. The more ozone, the better, to be honest. We actually have a few installations and a lot of experience with ozone, and we love it. It actually hydraulically increases the performance of the membrane significantly. So any ozone application is really a good fit for ceramic membranes.
I have to apologize. I sent just the link for the PFAS report just to one person. I have to, do it for everybody. Sorry, guys. Here's a link to the PFAS report for everybody. Final question. Why is lifetime limited to 20 years?
I'm not sure the lifetime is limited to 20 years, but the warranty is limited to 20 years. And I think that's probably more of an accounting question than it is an operations and materials question. I don't think there's anything that's going to keep these from operating longer than that.
Yeah.
Final question. Can the filters handle red tide seawater?
No problem. Yes, seawater is a big focus area for us. We've done some very positive results there already in pilot studies, and more is to come in the future. But the short answer is yes.
Perfect. I think we are done. Are there any further questions from the audience? And please put it right now into the chat. Otherwise, hey, we have 59 minutes, so we are really close to the 1 hour we already, try to keep. Thanks, everybody. Thanks, our speakers. Thanks, Kai, Chris, and Julius for being here, and also the audience for watching us. This video, or let's say this presentation, is recorded, and we will put this on the YouTube channel from the 𝘴𝑒𝑟𝑎𝑓𝑖LTAC company very soon. So if you do have any further question, just go in. Furthermore, just follow our PFAS week on LinkedIn, and there also you will find all the single individuals, which are our speakers. And if you do have any question, just drop them a message directly. Yeah, produced water treatment. Last question. Produced water pre-treatment. Yes.
Yes.
Chris is nodding.
Also more to come there. The answer is yes.
Perfect. Thank you, everybody. Thanks for joining. Thanks for being here. Thank you, everybody. Have a safe trip home. Mostly you are just in the office or at home. Take care. Goodbye. And I will close now the meeting. Bye-bye.
Bye-bye.
Thank you all.